Hey, wonderful class. We're gonna do practice exam number 3. So, yeah, let's get started. All right, one of the things I asked you to do, which are pretty important, is memorize the strong acids and strong bases. And that's gonna help you recognize how to answer a lot of these questions. So again, just it's not negotiable. If you want to do okay on this test, you have to have these memorized. So let's do strong acids and strong bases. And the good thing is on the periodic table, both of these kind of have some patterns. So the strong acids, in fact, I'll pull up a periodic table here. All right, so the strong acids are going to come from this halogen group right here, chlorine, bromine, iodine, at least 3 of them do. So that's going to be part of the strong acids. And then the strong bases are going to come from over here. So we have lithium, sodium, potassium, calcium, strontium, barium. So kind of like that little order right there. And I like that because a lot of other books have even more and they don't actually make a lot of sense. So cool. So our strong acids would be HCl, HBr, and HI, like we talked in class. Claire brought ice. All right, and then we also have HNO3, H2SO4, and HClO4. All right, and remember, strong acids, what's important about them, in fact, I'm going to write this down right now. I think it'd be nice to have it in one place now that we've covered everything, is that you can calculate the pH from them right away. So if you're given a concentration of one of these, you just take the negative log of that concentration and you have the pH right away. Another thing about them is they make neutral anions. What I mean by that is chloride, bromide, Cl negative, Br negative, I negative, NO3 negative, SO4 negative, and ClO4 negative would all be neutral anions. All right, so if you just take an H off of these guys, you get these, and these are all neutral anions, meaning they have no pH issues whatsoever. They don't contribute to the pH at all. Another thing is that they have a one-way arrow. One-way arrow. And part of that is because these are really weak. So like if you have HCl and it breaks down to H plus Cl minus, because this is neutral and not a base, it can't go the opposite direction. And so it only goes just one single direction. That's our strong acids. Then we have our strong bases. Again, you can look at the periodic table. We have lithium hydroxide. We have sodium hydroxide. We have potassium hydroxide. I don't know about you, but I was looking for ways to memorize things, and I was just like, yes, you have LNAC. The neck for memorizing things instead of like the neck, neck. I don't know, but however you're gonna memorize it. And then we have strontium hydroxide, calcium hydroxide, and barium hydroxide. So, srukaba, I don't know what that would be, but however you're gonna memorize it. So these are gonna be our strong bases. The beautiful thing about them is you can calculate the OH right away. Because they wouldn't even need to calculate it. Let's do pH. Let's do POH. You can calculate the POH because whatever concentration these are is going to be the concentration of the OH minus. So you can calculate the POH right away. They also make neutral cations. So for example, lithium, sodium, potassium, strontium, calcium, barium ions. None of these contribute to the pH whatsoever. So, same exact concept over here. If it breaks down, it's going to be a one-way arrow. Cool. All right, so these are acids. Acids give off H+. By Arrhenius definition, bases give off OH-. Okay. With that being said, we can now read this question. It says, which of the following has the weakest conjugate acid? All right, so when we're looking at this, I immediately see all three of these were on that list, right? These are all strong bases. And what did we say about the strong base conjugate? Their conjugates are neutral. So when, again, sodium gives off when sodium gives off its anion, or its cation right there, we know that that's neutral. The only one that's not on that list is this one, aluminum hydroxide. And aluminum hydroxide breaks down to aluminum and 3 hydroxides. This is not neutral. Therefore, this must be a weak acid. And our arrow would actually go 2 ways. Here our arrow would go 1 way because it's strong. Here our arrow goes 2 ways because this was not on the list. It's that straightforward. All right. Now it says consider a reaction that is this. What happens if you add more C? So when I get to an equilibrium reaction and I see some sort of enthalpy, I like to add it to one of these sides because I can treat it like a product or I can treat it like a reactant without having to think too much about it. So here you have a negative. Remember, negative means that it's exothermic, meaning it's this reaction, when it happens, it gives off heat. Therefore, heat is one of the products. So I would add I'm actually gonna even just get rid of this, plus heat. So heat's going off this way. If it had been positive, I would have written the heat over here on the reactant side. All right, so that gets rid of that for me, and I feel better about that. Now we can kind of read through. It says, what happens if you add more C? Okay, so if you add more C, remember, anything that we add, it's gonna go the opposite direction. So if we add more C, it's gotta go to the left. This is Le Chatelier's principle. What happens if you take away C? Well, if we reduce C, the reaction is gonna go try to fill in that void. It's gonna go to the right and try to fill in what we just did. What happens if you add heat? So I think we ended on a decent note in lecture, but remember this is a concept that I don't want you to overthink. When we added more C, the reaction went that way. We know heat is a product, so if we add more heat, the reaction is going to go that way. It's just treated just like a product or just like a reactant. You don't need to overthink it at all. So if you add heat, the reaction has to go to the left. All right, what happens if you reduce the volume or increase the pressure? Both of those things would kind of be work together. So if we reduce the volume or increase the pressure, now we have to look at the moles of gas. Over here on this side of the reaction, I have 5 moles of gas. And over here I have 2 plus 3. So anytime we talk about pressure, you need to think about mole of gas, okay? So we have 3 moles of gas going to 5 moles of gas. If we increase the pressure, we give it more space to expand. So if we give it more space to expand, it's going to create those more moles of gas. And we're gonna end up going this way. But if we decrease the pressure, it would have gone the opposite direction. So if we squeeze them all together, they go to the smaller number of moles of gas. All right, yay, I think we're done with that. Now it says, which is the strongest acid? All right, so none of these are on our list of strong acids. So we talked about another concept that was anytime we have a hydrogen, the more electronegative things it's bonded to the right, the stronger it's going to be. And that's just because if you have like oxygens over here or something to that effect, they're taking off they're taking all the electron densities toward them. Now, if this was bonded to like a carbon and a hydrogen, it wouldn't matter because remember, carbon and hydrogen are not electronegative. But because oxygen is electronegative, the more oxygens you have, the more that separation is going to be, the greater that separation is going to be. And that's why this is going to be your strongest acid. Let me see how I do this. H bonded to more electronegative things. Again, that's just because those electronegative things, those oxygens, are pulling the electron density toward them and very far away from that hydrogen and making that easily come off. Okay. Oh. I lost the practice exam. Where'd it go? Okay, fine. There you go. So, number 4 says you want to prepare a buffer. And it's going to be a pH of 3.53. So, it asks you which one's best for this. Now remember, you want the pKa of a buffer to be pretty darn close to the pH. For a buffer, you want the pKa to be pretty darn close to the Ka. So if we went through and calculated the pKa, remember P means negative log of. Essentially, for this first one, for example, we'd say the negative log of 1.8 times 10 to the negative 4 equals, and then we just do that. So let's turn this on. Negative log of 1.8 times 10 to the negative 4. It should be about 4, and we get 3.74. We do the same for all these. 3.5, negative log of 3.5 times 10 to the negative 7. And you get 6.45. You do the same for the next one. Negative log 6.16 times 10 to the negative 10. And you got 9.2. So you didn't even have to actually calculate these. And here's why. You can look at the exponents right here. 4, 7, and 9. And that tells you the pH is going to be close to 4, or pKa, excuse me, is going to be close to 4, to 7, or to 9. All right, so you want to find the one that is closest to that. Which one's closest to that? That is this. And the A would be the answer that you'd want to choose because that's going to have the best Ka to keep things in the buffer range that's around the pH that you want. All right, number 5, it says the following reaction has a K of 4.7 times 10 to the negative 2 and initially contains this, this, and that. It says which direction will the reaction proceed. All right, so if you're like me, you saw the word initially and you want to write an ice table, right? But then it asks you what direction will it proceed. So that's kind of a clue that it actually wants you to do Q. Okay, so if it asks you which way it's going to go, to the right or to the left, that's when you're going to want to do Q. And if you remember, Q is just like K, except you calculate it and see where everything is for that point in time. So our Q would be equal to, for example, C to the 4th, concentration of C to the 4 over A times B squared. So we set it up just like we would a K, products over reactants. Let's go ahead and plug some things in. Our C is 0.0018 to the 4th, all over 0.53 times 0.99. Okay. And if we calculate that, and it was 0.53 squared, sorry, or 9 squared, I got it. So when we go to calculate it, I'm going to do 0.0018 to the fourth. I'm going to divide that by 0.53 times 0.99 squared. I get an answer of 2.02 times 10 to the negative 11. I'm going to do it one more time just to make sure. The fourth, although I can tell it's going to be a really small number no matter what. Divided by 0.53 times 0.99 squared. I get the same answer. Great. So this is our Q, right? This, you can't see that very well, but that's a negative 11. All right. So a very, very, very small number. Small. Because our K was 4.7 times 10 to the negative 2. This is much bigger. This has 10 zeros in front of it, and this only has 1 0 in front of it. All right, so this one's bigger. Remember in class I said it's almost like preheating an oven. You're watching this reaction happen. Right now it has these concentrations that we have right here. So this is 0.53, 0.99, 0.0018. And the reaction's occurring. So it's going to be going to the right or to the left. We don't know. But we do know this, that this is bigger. What that means is that there are more products than reactants. More products over reactants than there are over here. So this is like a really, really, really low number, and it's got to keep getting bigger in order to get to this one. So the reaction is going to proceed to the right until we're cooked. It's not cooked all the way. It's the oven's just barely preheating. We got to cook it till we get here. Now, if this number happened to be bigger than this one, then we know it has to proceed in the opposite direction. And if they're equivalent, then we know that it's at equilibrium. So if we had calculated Q and found it was this number, it had to have been at equilibrium. All right, number 6. I think I'm gonna need some paper for this one. The following reaction has a K of 1.8 times 10 to the negative 7. It gives you some initial concentrations and asks you to find C. Okay, so now I see it gave me initial concentrations. I'm gonna rewrite it. Now I see it gave me initial concentrations, and it didn't ask me which direction it will proceed, so now I can do my ice table. All right, my initial A is 0.14. My initial B is 0.33. It doesn't give me any information. Good luck finding C. I don't even see C. Let's go ahead and make that D, just to make our life easier. And this has to be 0.00. I'll fix that and re-upload it. All right, so it wants us to find the concentration of this one at equilibrium. All right, so we know the K, but we don't know how much each of these is going to be losing or gaining in order to reach that equilibrium. So in that case, that's where the X comes in. We don't know how much that would lose. We don't know how much that would lose, but we know for every one of those, we must have 2 times the amount of those. And we also know that this is going to gain some X, 2X. There. And so at equilibrium, we have 0.14 minus 2X, 0.33 minus X, and 2X. We know that no matter what happens, we have to have this K as our products over reactants. So 1.8 times 10 to the negative 7 has to equal our products over reactants. Our product, by the way, is going to be this D squared over A squared times B. Right? So if we plug and chug these numbers at equilibrium, put this 2X into there, we have 2X squared all over 0.14 minus 2X times 0.33 minus X. Now, if we foiled these, if we put them together, we'd have that times that, that times that, that times that, that times that, and you'd end up with X and an X squared. Anytime we have varying powers of x. So down here I would have x and x squared, and up here I'd have x squared. We're going to say that this number is small. We're going to get rid of it. Because this x, when we subtract it from that 0.14, it won't make any difference because this number is going to end up being so small it won't matter. And I especially know that because the Ka is very small, which means this number is going to be very small at the end. So we get rid of it. That simplifies things a lot, and this should be squared, by the way. So this 2 is distributed there and there. So we have 4x squared all over 0.14, which is squared, times 0.33. And that's equal to 1.8 times 10 to the negative 7. And hopefully that simplifies things, so now we can kind of figure it out. So again, from the top briefly, we saw the word initially. It didn't ask us which directions it's going to proceed, so we have to do an ice table. We lose all our x's, we gain our x's, put it together, and then we know that anything we're subtracting or adding is generally going to be pretty small comparatively, so we get rid of it. All right, so now let's go ahead and solve. 1.8 times 10 to the negative 7. I'm going to multiply it by 0.14 squared. And then I'm going to multiply it by 0.33. So now I move these guys over there. So now they're over there. Now I have to divide it by 4. And then now, last but not least, I have to take the square root. And I get 1.7 times 10 to the negative 1, 2, 3, 4, 5 mole per liter. And that equals x. All right, I'm gonna do it one more time in case you guys got something different. Okay. And I get the same thing, so I'm comfortable with that. I'm gonna go with it. And so that gives us x. That's not our answer though, yet. Our question was asking for the concentration of D at equilibrium. Well, we know that D was actually equal to 2 times x, right? So at equilibrium, we look for D. At equilibrium, this is just like a chart, right? And that's what we're looking for. We solve for x, so we know that the concentration of D must equal 2 times 1.7 times 10 to the negative 5. So I'm just going to do 2 times my last answer. And it's 3.4 times 10 to the negative 5, which makes sense. All right, again, pretty small number. You could calculate that in respect to what you subtracted it from and ensure that it's less than 5%. But I don't believe I'm giving you any problems like that, and I certainly is not my intention if I ever do. All right. Number 8, calculate the pH of a 4.65 mole per liter solution of weak acid HBrO. All right, the reason I did HBrO is because I saw a lot of people seem to be kind of worried about all the things you see. But the important thing is that you've got this H, and you've got something else you don't care about, and like that doesn't even matter. And so I kind of want to go through and show you that. Oh, I hear little feet upstairs. My babies are waking up. All right, so it says calculate the pH of weak acid H blah blah and da 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 da. All right, so it's a weak acid. If it had been a strong acid, we could have just taken the negative log of that and we would have had the pH. It would have been that straightforward. But this is not the case. So we know our Ka is equal to that, and we also know that H blah blah I'm going to actually write it out. Plus water will make, remember, any weak acid is going to give off the H to that thing. H3O plus, plus, blah, blah, minus. Okay, so when we're talking about a weak acid, it doesn't matter what it is. This could be anything. The H goes there, we get that, and we have whatever's left is going to have a new negative charge on it. Okay, so if we go to do an ice table here, our initial concentration of this is 4.65, but we know not all of it's going to react. If it had been a strong acid, all of it would have reacted, and that's why we'd be able to do this. In order to calculate the pH, we need to find the H3O plus concentration at equilibrium. So we're looking for this number here, whatever that ends up being. That's the important part, and that's how we're going to calculate our pH. Remember, because pH is an equal log of that. All right, so we have 4.65. We know we're going to lose some X there. We don't care about water. We're going to gain some X here and gain some X here. These would be 0 at the start. So we get 4.65 minus X. We get X and X. Okay, so we're solving for X, and then we'll take the negative log of it, and we'll have the pH. All right, so we know the Ka is 4.2 times 10 to the negative 9, and that would equal our H3O plus times our blah blah minus all over H blah blah. In other words, X times X, put this one in there, that one in there, which would give us X squared, all over 4.65 minus X. We're subtracting a small number from a bigger number, that's 0. All right, so now we have 4.2 times 10 to the negative 9 equals X squared over 4.65. So, all right, so I'm going to do 4.2 times 10 to the negative 9 times 4.65, and then I've got to take the square root of it. And I get an answer of 1.4 times 10 to the negative 1, 2, 3, 4. I'm going to do it again just to make sure. I had 4.2 times 10. My decimal doesn't work very well on this. 4.2 times 10 to the negative 9 times 4.65. And then I'm going to take the square root of that. Again, I get the same. Okay, so this is our X, and remember, X is our concentration. So this also equals our concentration of H3O plus. We know that the negative log of H3O plus equals the pH. In other words, the negative log of our answer will be the pH. So I'm just going to say negative log of that answer is 3.85. And remember, we know for a weak acid it's generally somewhere between 3 and 5. And so we might have even been able to guess that depending on what the answer choices were. All right, ooh, we're getting through it. Last two. Okay, find the KSP of silver chloride if the molar solubility is that. So I wanted to go through these last two questions just because we rushed them in lecture a little bit. So remember that molar solubility, we're looking at how a solid breaks down. So if we have like silver chloride, it's actually in equilibrium with silver and chloride. And these are slightly soluble things, meaning if you put them in water, mostly they'll remain solid, but a little bit will dissolve. And what this molar solubility tells you is how much each one's going to dissolve. So it's saying, hey, you'll get this much silver and that much chloride. If I had had a 2 here or something like that, it would have been 2 times that amount. Or if I'd had a 3 there, it would have been 3 times that amount. What I mean by that is this is 1.33 times 10 to the negative 5, and this would be 1.33 times 10 to the negative 5. So it's kind of telling us an x in a way. So if, again, this had been a 3, I would have done 3 times that concentration. So it wants to know the KSP. KSP is always products over reactants, but the reactant here is a solid. So it's just going to be the products multiplied by each other. It already gave us our x, or we call it S when we're talking about solubility. So that's 1.33 times 10 to the negative 5 times 1.33 times 10 to the negative 5. In other words, 1.33 times 10 to the negative 5 squared. So I'm going to do 1.33 times 10 to the negative 5, and I'm going to square it. And I get an answer of 1.77 times 10 to the negative 10 would be our molar solubility for that. It works just like an equilibrium thing. Equilibrium constant. Okay, I'm going to do it one more time just in case I messed up. 1.33 times 10 to the negative 5, and I'm going to square it again. Perfect. I get the same answer. All right. Now let's do that backwards. I'm giving you the KSP, and I'm asking you to solve for the molar solubility. Okay, so our KSP is 5.60 times 10 to the negative 10. And that's going to be equal to the products over the reactants. So if we have strontium carbonate, it's SR2 plus. I can do a better job here. SRCO3 is going to break down into SR2 plus and CO3 2 minus. Or again, this one won't matter. This would give us some S, and this would also give us an S. If these had coefficients in front of them, it would have given us 2S or whatever, like we did in class. And we know that this is equal to our products divided by the reactants, which are none, that we can write. We just plug these in, just like we would like x times an x. In other words, x squared. So right now we have 5.6 times 10 to the negative 10 equals x squared. We're solving, or sorry, I should write s. That's just a habit. We have 5.6 times 10 to the negative 10, and we're trying to get this s squared. So 5.6 times 10 to the negative 10. And then we want to square it. Just kidding. We want to take the square root of it. Sorry, I'm listening to what's happening upstairs. And I'm almost done to the negative 10. And we want to take the square root of it. I get an answer of S is equal to 2.37 times 10 to the negative 5. That makes sense. I know that answer is right because 5 plus 5 equals 10. All right, cool beans. So that would be the molar solubility. In other words, the maximum concentration, if you took some strontium carbonate and you dissolved it in any amount of water, in a bucket, in a drop, in a huge pool of water, it doesn't matter. The maximum concentration that you could get out of that water at a particular temperature, this being probably 25 degrees Celsius, is that. That's the maximum concentration you can get no matter what. So it's pretty cool, as long at a saturated point. All right, I think that's it. All right, guys, I hope this helps. Let me know if you got any questions, and good luck studying.